Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook over.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a second video on graphs of polar equations. In this video, we're going to graph polar functions of the form r of theta is equal to some number times the sine of theta or some constant times the cosine of theta. You should have watched my video on the general idea behind graphing polar curves. It's only like a 16-minute video or something like that. And it just gives a general idea of how I graph. Eventually, you graph enough of these, you're going to know what they just look like by looking at the form. But when you're new to graphing polar curves, it's good for you to develop a method that will always work when graphing polar functions of these forms. And the method that I teach in the previous video and that I'm going to use in this video always works. Now, before we jump into this, like I said, you will eventually graph enough of these that you will not have to go back and do my method. You'll just be able to say, oh, this is a circle of radius 3 along the y-axis. That's exactly what it is. It's just that you don't know that yet because maybe you're new to polar functions and polar curves and graphs of them. That's totally fine. So how would you graph them in general, just in case you forget? Well, the first thing you would do is trade that function out for the Cartesian or rectangular equation, y is equal to 6 sine of x. And we're going to graph that first. So I'll just quickly sketch out a graph. It doesn't need to be perfect. It's a sine curve. We happen to know that because the amplitude is 6, it reaches a height, a maximum of 6, and a local minimum or a minimum of -6. And then you can label the angles, the important key points, if you will. And you don't actually have to label all of them, but I just have a habit of doing it. This is a great method anyway to practice graphing trig functions, because as we move forward, we're going to change the period here. We're going to add numbers, that type of thing. And so this is great practice for a final exam for graphing, because on finals, you're going to be expected to be able to graph all types of trig functions. Once you're done with that, you just go over and plot the pole and the polar axis. You don't have to be, well, I mean, it's nice to be somewhat accurate there. And then you go back to your Cartesian or your rectangular graph here. And you, the way I always described it is that you're standing on this line here. This is the x-axis, obviously. And you're just throwing rocks in front of you or behind you as you walk through these angles. So for example, at an angle of 0, you just drop a rock at your feet. So again, at an angle of 0, remember in the polar coordinate system, the angle is the direction you're facing. So when I'm facing an angle of 0, I'm going to drop a rock at my feet. Then, as you increase your angle, you see you're throwing rocks in front of you until eventually they reach so far in front of you that at pi over 2, they are 6 feet in front of you. So I will go ahead and start turning through angles in the polar coordinate system. And as I do so, I'm going to start throwing rocks in front of me until eventually when I face an angle of pi over 2, they're 6 feet in front of me. So I want that distance to be 6 feet in front of me, or whatever you want to call it. But otherwise, it'll be a nice smooth arc of rocks that get thrown in front of me. And even that is not the nicest arc of it, but whatever. And so you can see that as I'm turning through an angle here, I continually throw rocks. They get further and further away from me until they're at their maximal distance when I'm facing an angle of pi over 2. let me go ahead and make that nice and smooth. So just do this here and do this here. There we go. And then I go back and I continue with this statement, right? So as I turn through an angle beyond pi over 2, notice I'm still throwing rocks in front of me, but the distance becomes less and less and less until by the time I'm facing an angle of pi, I drop a rock at my feet. So again, I'm going to turn through angles, and as I turn through angles, the distance that I'm throwing rocks gets less and less and less until essentially I'm dropping a rock at my feet. So it looks something like this. There's a symmetry to this picture, so I'm trying to make it as symmetric as possible. And it goes back to here. Now, often I like to encourage my students to draw the path of travel. That is, as you're turning, I'd love to see kind of that path of travel there. This is going to help out for future topics in both pre-calculus and calculus. So kind of drawing out that path of travel is really nice to do. By the way, and I mentioned it in the previous video, but if we continued beyond facing this angle of pi, we would start throwing rocks behind us until we were facing an angle of 3 pi over 2 where we're throwing a rock negative or throwing a rock 6 feet behind us. So once I turn to face an angle of 3 pi over 2, I will have thrown a rock 6 feet behind me. If I'm facing this angle, I'm throwing a rock this far behind me, and so on and so forth. So you could see that we're actually just retracing our curve when we go beyond the angle of pi. And that does happen quite often in polar coordinates. And it does become an issue in calculus, because in calculus, you want to know what is the length of that curve. And if you try to figure out the length of that curve by starting at 0 and ending at 2 pi, you're actually going to count that length twice. So in calculus, you end up having to worry about when do I start repeating my redrawing process. But in trig and in pre-calculus, you don't really have to worry about that. You could just draw a single rotation there and you get the entire curve. All right, some things I want you to notice about this so we can start pattern recognition. This is a circle, actually. That is going to be a circle. And the radius of that circle, if this distance from bottom to top is 6, the radius is a radius of 3. So this circle is what I would call a radius 3 circle. Or you could say a diameter 6. That's another way you could say it. Radius 3 circle. And I say on the positive y-axis. Oops, y-axis. It's not really on the y-axis because we're dealing with the polar coordinate system, but you get the idea. It's on the positive y-axis if we were to superimpose a rectangular system on that. And notice r is equaling 6 times the sine of theta. Sine is always associated with y values. I shouldn't say always. That's those types of definite statements often get broken. So y is often associated with the sine. And notice this curve is lying on the positive y-axis. So that's the circle on the positive y-axis of radius 3 or diameter 6. All right, let's do another example. Now, if y is associated with sine, then x should be commonly associated with the cosine. And if in that previous case we had a circle on the positive y-axis, we should be able to imagine that we will probably get a circle here on the x-axis and maybe on the negative x-axis. Well, let's find out. Let's go ahead and just graph -2 cosine of x. So y equals -2 cosine of x. And we'll go ahead, just do that really quickly. It's the upside down cosine, so it looks like that. It reaches a maximum of 2 and a minimum of -2. And remember, this is 2 pi, and here's pi, and so on and so forth, right? Once I'm done there, I just plot my pole. You can do it off to the right or down below. It doesn't actually matter. And now let's see what happens as we're facing an angle of 0, when x is 0. Notice you're throwing a rock behind you 2 feet. That's kind of weird. So I'm facing this angle of 0, this direction right here, but I'm going to throw a rock behind me 2 feet. 1, 2 feet. Let's just say that's 2 feet behind us. So there we go. That point, if you really wanted to label it, which I personally wouldn't want to, but whatever, you could say that's a radius of -2 when you're facing an angle of 0. Okay. Then, as we increase our angle, so as we rotate counterclockwise, we're still throwing rocks behind us, but they're getting closer to our feet until when we're facing an angle of pi/2, we're dropping a rock at our feet. So again, by the time I face an angle of pi/2, I will have dropped a rock at my feet. Between the angle of 0 and pi/2, so for example, when I'm facing this angle, this direction right here, we're throwing rocks behind us. And they start actually pretty far behind us and then get smaller and smaller distances as we turn through this angle. Again, because these distances right here get shorter and shorter. So as I turn through that angle, initially I'm throwing a rock pretty far behind me, but then as time goes on, it gets closer and closer to me until I eventually drop a rock at my feet when I'm facing this direction. So the path of travel looks something like this. And then, as we move or turn past the angle of pi/2, we start throwing rocks in front of us until by the time we're facing the angle of pi, we throw a rock 2 feet in front of us. So again, as we turn through these angles here, I'm facing these directions, whatever they are, right? We're throwing rocks far out in front of us, or further and further out in front of us. So initially, the rock is at our feet, and then as we turn through an angle, the distances grow until they're pretty far out in front of us, and they continue to get further in front of us until they're 2 feet in front of us. And the path looks something like this. I'm trying to make it circular because, to be honest with you, it is a circle. And there you go. And at that point, it actually just starts, the pattern starts to repeat. So at pi, it starts to repeat, and you can kind of see it, right? If you're facing an angle of pi now, and you start to continue to move forward, now you're just going to keep throwing rocks in front of you, but they get closer and closer to your feet until you're facing an angle of 3 pi/2. So imagine you're facing an angle of pi, you throw a rock 2 feet in front of you, they get closer and closer and closer to you until you're facing an angle of 3 pi/2. That's this angle right here, and you're dropping a rock at your feet. So it just retraces the curve at that point. Again, pattern recognition. Notice it's a cosine, and we have a circle that's on the x-axis, and it's on the negative x-axis, and it's a negative cosine. So a good rule of thumb here, kind of the punchline to this statement, is the following. The graph of r equals a sine of theta is a circle of diameter absolute value of a that is on the positive y-axis if a is greater than 0. It's on the negative y-axis if a is less than 0. The graph of r equals a cosine of theta is also a circle of diameter absolute value of a, and it's on the positive x-axis if a is greater than 0. It's on the negative x-axis if a is less than 0. Also, you should note they both go through 0, 0. So these both, I guess I should say, put it this way, these both go through the pole. There you go. You can easily see it there. So our r equals the -2 cosine of theta is a circle of diameter 2 on the negative x-axis, and it goes through the pole. Pretty pretty nice. And it actually works well with the other example as well, right? 6 sine of theta is a circle of diameter 6 that is on the positive y-axis, and it goes through the pole.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.